Hello, and welcome to the third part of Lesson 1 of CE 3305, Engineering Fluid Mechanics. And the topic of this third part is essentially the definition of a fluid, a look at units and continuums and so forth. And that pretty much concludes a major part of the first lesson in Chapter 1. So the video link will be located here. Excuse me, part 3. And if I clicked on it now, nothing would happen because it doesn't exist yet. And let's go to the readings, and we want Chapter 1. I'll adjust the size a little bit. Hopefully I won't regret that. And we want to first examine this sentence right here. So, in terms of words, a fluid is a substance whose molecules move freely past each other. More specifically, or in the terms of mechanics, it's a substance that will continuously deform under the action of shear stress. Now bear in mind that a solid can deform under the action of shear stress, but does not flow like a fluid. Both liquids and gases are classified as fluids. Now this picture here, table 1.1, presents a good visualization and classification of the differences between the three most commonly encountered states of matter that we encounter as engineers. So there's some other states of matter not here. For example, a plasma is a type of gas, but it's not entirely a gas. And there's various versions of solids and liquids at peculiar pressures and temperatures that are not commonly experienced in the terrestrial environment. So, first, a solid, you can imagine it as a lattice of molecules, or atoms if it's an element, that's arranged in a pattern and essentially maintains its own shape at the temperature and pressure of examination. Solids don't need a container. The molecules themselves are relatively immobile because they're held together with strong intermolecular forces, and the density of solids is relatively high. For example, steel is 7,000 kilograms per cubic meter. The spacing between molecules is small. If we apply a shear force or shear stress, the solid will deform to the point that it can resist that shear stress, and then it stops deforming. And we'll draw some pictures of that shortly. The normal stress causes deformation that may or may not produce a volume change and causes failure. Best example of that is when you break concrete in the materials lab. We apply very high normal forces to the concrete, and eventually the solid, and concrete's a composite material, so it's comprised of a bunch of different kinds of molecules. The solid can't resist that normal force, and so it fails. It has no concept of viscosity because it doesn't flow, and they have very high bulk compressibilities. Again, steel is 160 billion pascals. Let's now consider the second column of the table, the liquid column. In this case, the molecules of the liquid have a little more spacing and they can move around one another, and they need a container to hold them, otherwise they spread out as far as they can until they make a monomolecular layer. The liquid will assume the shape of the container, and if the container is open, the liquid will stay in the container. So your cup of coffee is a good example of a liquid. As you tip the container, the liquid will move under the forces of gravity. As long as you don't tip it so far that the liquid has a desire to leave the container, it'll stay in the container. The density is moderate. For example, water is 1,000 kilograms per cubic meter. The molecular spacing is small, but not as small as a solid in that the molecules can move around. The effect of shear stress would cause it to flow, and the effect of normal stress will produce a deformation associated with a volume change. Some of those certain kinds of liquids are very difficult to compress, but they can be compressed. The viscosity is high, and the viscosity is temperature dependent and will tend to decrease as the temperature increases. So if you want to make molasses flow easier, you increase its temperature. Lower viscosity, easier flow. Viscosity later on we'll see as a measure of how easy things flow or don't flow. Compressibility is moderate. For example, the bulk compressibility of water is 2 billion pascals, so 80 times less than that of steel, but still not easy to compress, and that's why liquids make good hydraulic fluids for hydraulic machinery. The last state is gas. The molecules are not particularly close to one another, and so they can fly around looking for things to hit. They'll expand and fill a closed container, and they'll uniformly distribute throughout that container. Now, if there's already gas in there, they'll share space with that other existing gas, and their quantity, the number of moles of gas A and the number of moles of gas B, each exhibit a partial pressure associated with the molar quantity of those two gases, and then the two partial pressures add up to produce the pressure that you would measure on an instrument. The typical density of gases are pretty small, so air is a little over a kilogram per meter cube. So if we look at that, gas is 1,000 times less dense than a liquid. A liquid is 8 to 10 times less dense than common engineering solids. Molecular spacing is large, the molecules are far apart, things fit between them. If we apply shear stress, the gas will flow. If we apply normal stress, the gas will easily deform. In fact, the ideal gas law, the equation of state, succinctly expresses that observation. The viscosity is low, so gas flows really easily. If we increase the temperature, the viscosity gets larger, according to this table. So to make gas more viscous, we increase the temperature. Gas is easy to compress, so the bulk modulus of gas at a room temperature is about 100,000 pascals. So again, looking at the density and compressibility, gas is 3 is H, 10,000 times more compressible than a liquid. A liquid is 80 times more compressible than a solid. Now those ratios aren't hard and fast, they'll vary for materials. So let's examine some of those principles in a drawing context. So imagine we have some plane here, and we have an element of material on that plane, and this material is what we know as a solid. Imagine an identical plane, an equivalent element of material, and this one we're going to call a fluid. And if we look at the block, either block, we're going to apply force to the top face. There's a vector that represents the area, the shaded area, and we're going to apply a force tangential to that plane that's pointing outward. So on the solid, if we apply that force, solid's pretty easy to imagine. Put a little bit of JB weld on a plate, glue the plate to the top of the solid, glue the bottom of the solid to the plane, and then yarn on it. And we apply the force, the solid's going to deform a little bit. But as long as that force is less than what it takes to destroy the solid, it will deform only as far as it has to resist the force. And the distance it deforms here will be a distance epsilon. That distance is called the strain, and the force divided by the area is called the stress. So the strain is proportional to the stress, and we'll call that stress tau, the shear stress. The strain is going to be some function of the shear stress, and for example, that function might look something like a stress-strain diagram. So stress would be, stress increases, yeah. And we head back in, and I guess we go to elastic, and then we go to destruction. Back in your materials class, you would apply, I'm plotting stress and strain this way, and that may be opposite to what you're accustomed to. But this range, when the stress is removed, the strain will go back to original conditions. If we go out to the too far, if we overstress it, when it comes back, it will have a permanent deformation. Okay, that's a solid. The other important thing is that the change in strain with respect to time is equal to 0. Once it reaches its new equilibrium, it stops moving. So to summarize that, we have the properties that the solid will deform, but not continuously. When we apply stress, the deformation is proportional to that stress, and that's called the strain. The strain is some function of stress, and assuming the solid does not fail, then that deformation is largely time invariant, and assuming we don't go beyond the elastic capacity of the solid, the process is reversible. When we remove the shear stress, the material returns to its original position. Now we're going to play the same game with what we call our fluid element. So we apply our force, and if we start to examine it over time, in the first few moments of force application, perhaps it deforms to that position. A few moments later, that position. A few moments later still, that position. And what we discover is that there are different stresses, different strains associated with different moments in time. As before, the strain is still proportional to the shear stress, but we also notice that the change in strain with time is no longer 0. So these two imply that Strain is some function of now both shear and time. Now this is key, so they're not time invariant. The fluid deforms continuously as long as the stress is applied. The fluid will continue to deform. The strain is still proportional to stress. The strain is now time variant. So to stop further deformation, we have to remove the force. But unlike a solid, it's generally not reversible. Removing the force, the fluid is not going to willingly go back to its original position. So that's the difference between a solid and a fluid. I have no stress-strain diagram for a fluid that would make any sense, so there's no attempt to draw it. So things that are fluids that were common in our everyday life: water, air, gasoline, ice cream, although arguably it's in emulsion, paint, paraffin, wax. So at 20 degrees Celsius, paraffin is pretty solid, doesn't need a container. At 90 degrees Celsius, almost the boiling point of water, paraffin is most definitely a liquid and needs a container. So there's a lot of things in our everyday lives that are fluids as we know them, and some of those things can switch between what we would call a fluid phase and a solid phase. Now, fluid mechanics, this class, is the study of motion, deformation, mass, momentum, and energy, and related properties of materials that cannot resist shear stress, aka liquids or gases. Mass, momentum, energy, and properties. Of materials that cannot resist shear stress. It's sort of a simple definition that encompasses an awful lot of information. Okay, the calculus of fluid mechanics, the mathematics of our book, uses continuously differentiable functions, and that use implicitly assumes that fluids are continuums. So we go back to the reading. And we have some discussion on continuums. The continuum requires a concept of a averaging volume that's large enough for continuum behavior to exist, but small enough so that we're not picking continental size differences. And I have a nice sketch to illustrate that. So imagine a collection of molecules. So I'm using my special Heisenberg telescope that can look into materials. We'll turn them into water molecules so they look like little Mickey Mouses. Okay, so there's a bunch of little water molecules. Now let's take an averaging volume. We'll take a small one because we want it to be molecular sized. And I'm going to move it through this collection of molecules. We'll move it along that line. So at that location right there, there's no molecules. So we would write at this location the density, which is the mass per, let's call it differential volume. Actually, I call it a delta mass. This location, that's 0. So if we're to plot, well, we'll just leave that be. That location at 0. I'll move it here, 0. Move it here. Oh, look at that. I caught me a molecule. Non-zero. 0 all the way along the line. Put that volume, that averaging volume up here, run it along that line. Oh, I get one moment where I have a non-zero. Put it along this line and get non-zero, 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 0, non-zero, and so on. And so we would conclude, from as far as continuum mechanics, that averaging volume isn't very useful. It's too small. So we can go bigger. Let's make an averaging volume that's, in terms of area, 4 times as big, so it'll be 8 times the volume. Here we have 0. There we've got a non-zero value. 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 That's not a bad averaging volume. We could go bigger still, non-zero, non-zero, and so forth. And so if we're to plot the density as a function of averaging volume, when we have the very small volume, the density might be 0, or it might be very large. Get a little larger still, might be 0, might be large, and we would see things depending on the, might do something like that. And then when we get to continental scale, it can do stuff like that. And so this region here of usable volumes is called the region of the representative elementary volume. So when you come across the word representative elementary volume, all the author means is that whatever sample size we're using is big enough to get multiple molecules every time if we're sampling in the fluid, and the result is approximately constant for that particular material. So the usual definition would be that the mass density can be defined, and it's assumed to be controlled by the sampling volume. The lowest usable volume, a sampling volume, is called the representative elementary volume. And when this is true, when we're in this region, many of the principles of continuum mechanics of the book are adequate to describe fluid behavior. Now there's another way of considering fluid behavior, which is to examine individual particles, if you will. Now we don't necessarily go down to the atomic level for particles, but we might represent a fluid as a collection of parcels. So here is a parcel, and maybe it has 7 fluid molecules in it. And we examine how that parcel moves through space. There may be an adjacent parcel, a parcel here, parcel there. You have to speak a very special language called parcel tongue. Bad Harry Potter pun. And we might also have an area in space represented by this dashed line where we're interested in the behavior of the parcels going through that. If we're interested in this dashed line and we're counting parcels coming and going, and we don't really care about the identity of a particular parcel, we just want to know how many enter on this face and how many leave on this face. That's called a Eulerian reference system, for lack of better words. If, on the other hand, we're studying the behavior of individual parcels and the path they take, that's called a Lagrangian. Coordinate system or reference system. They're not equal to one another, but they both can be used to describe fluid behavior, and each one has advantages under certain situations. It's a special. The parcel method is especially useful um, when we're interested in a particular identity of fluids. So, Lagrangian coordinate system, the path the particle is going to take is important. The parcel will have attributes like position, x, y, z, t, and have a mass. In the Eulerian system, we have attributes like flow, discharge in, discharge out. Two different ways of looking at the same behavior. The volume of the parcel can be relatively large. For example, in air quality modeling, they might represent cubic kilometers. So this little box here could be a cubic kilometer. Or they can be very small, and in fact, there is research and supercomputers are applied to track the positions of individual molecules, at least for computational chemistry. But the ideas are the same, whether it's a cubic kilometer or computational chemistry. In fact, the parcel method is used to design wings and helicopter blades and turbine blades, where the parcels themselves represent small volumes of air, and they're applied to the various structures to come up with shapes of blades. And doing it in a computer is far more monetarily efficient than building scale models and running them in wind tunnels. Although usually the final design does get wind tunnel tested, because it's kind of embarrassing to have your plane fall out of the sky. Just ask Boeing. Some models can represent these parcels as drops, and they might say that, well, a million drops represents 1 watershed inch for hydrology. It's pretty researchy, but that's the idea between a parcel and Eulerian concept. In our textbook, I believe the word they use is particle. Liquids and gases, continuum. Yeah, what I just described is called the fluid particle. The dimensions and units we'll pick up in face-to-face, more or less. We'll have a quick discussion of it here before we conclude this third video. So dimensions and units. Easy to confuse because they're quite related. Dimensions are things that can be measured. Length, weight, temperature, speed, mood. Kidding, can't measure mood. Units is how much of a dimension is counted. And it'd be helpful if I was on the right deal. So, dimensions are things that can be measured, such as length, weight, temperature, speed. Units is how much of a dimension is counted. As an example, a meter is a unit of length. Length is the dimension. Meter is the unit. As an example, consider a table. And the table has some length. And we have several ways to measure it. We can take a laptop computer and we can lay the computer starting at one end of the table and just count how many laptops. 1, 2, 3, 4, 5. So this table is 5 laptops long. It's not a very useful measurement, so we decide, well, let's go ahead and use a person. So we got Stick Dude, and we have Stick Dude lay on the table, and when he does, basically we figure we can get almost 1 3/4 Stick Dudes long. Also not a very useful measurement. We can take a foot of some English king from a long time ago, and we can see how many feet it goes. 2, 3, 4, 5. And we can have 5 feet. We can take a meter stick with the original name on it, Napoleon, and we get the meter stick, and we can get 1 plus 3/4 meters. Okay, same table, same dimension of length. Depending on the units, we get different values. So 5 laptops, 1 3/4 Stick Dudes, 5 feet, 1 3/4 meters long. So it looks like Stick Dude is a meter tall, so he's kind of short. So that's the difference between dimensions and units. In most of our computations, we need the dimensions to work out correctly to have dimensionally homogeneous results, but we often use the units to keep track of the dimensions. There's something called a consistent set of units with various version factors. The 2 common ones are the imperial system, also known as U.S. customary. 3 nations in the world use it: the United States, Liberia, which is in West Africa, and I forget what the 3rd nation is. There's almost 300 nations on the planet, so we're looking basically 1% of the planet uses this U.S. customary system. The alternative is the SI, or the System International, also called the metric system, and it's just an alternative that's an international standard that, interestingly enough, the United States signed a treaty and agreed to use a long time ago, and just haven't gotten around to it. You want to use consistent units when possible because it reduces errors in your arithmetic operations. The SI system is usually preferred to U.S. customary because most of the unit conversions in the SI system vary by powers of 10. In other words, what's happening is you're moving decimal points left and right. And that's somewhat less error prone than the U.S. System, where you're both moving decimal points left and right, but instead of dividing by powers of 10, it's different numbers. For example, there are 12 inches in 1 foot, which doesn't break down very well when you're using decimal points to represent fractions of a foot. Be better if we made 1/10 of a foot, which is also a legitimate unit. Whereas in the SI system, a meter is built of 100 centimeters or 1,000 millimeters. Getting the decimal point in the right place is considered far easier in that system. There are some interesting things because the 2 systems. So the U.S. system is a force length time. So everything is, the forces are based on pounds, whereas the SI system is a mass length time, and so everything is based on the mass, which is a kilogram. They're easy to convert between the 2, and naturally, just to make life fun, there is such thing as a pound mass, and there is such thing as a kilogram force. So there's no conceptual fundamental advantage in one over the other. The SI is attractive because mostly you're dealing with moving decimal points to the right, to the correct location. All right, well that would conclude this introductory lesson, Lesson 1, and thank you for your attention. And we will move on to Lesson 2, and I look forward to seeing you in class.